Swayam Prabha. Digital India. Educated India.
Welcome everybody. We did a whole video on resonance and we're going to do some more practice. Practice is important for resonance because it takes a while to become an expert at resonance. So watch the previous one and then watch this one. So let's see some of the repetitive trends that you're going to see in resonance. What are they? You are typically going to see electrons moving from, as we said before, lone pairs become pi, pi's become lone pairs, and pi's become pi's. Just in different regions. Actually, they're already there. We're going to describe them like this, in this flow. So here, for example, if you have 3 carbon atoms, and we're only going to consider the lone pair electrons and pi electrons for resonance. The sigmas don't go anywhere. As I said, this is not a reaction. If the sigma moves, that means you're going to break or make a bond. That's a reaction. This is just description. These things don't really exist as discrete molecules. They're just descriptions. Okay, we're just drawing here. So here you have 2 electrons here. So 1 electron here and 1 electron here, and there's nothing in here. Basically what you're going to do, 1 here, and nothing in here. So these 2 are going to look at this and say, hey, it looks exactly like my house. Why can't I move in? And so they just move in. And they're in all 3 of these houses at the same time. So both electrons are in these 3 orbitals or regions of space, I squared. The probability of finding those electrons is 90% in these 3 regions of space, orbitals. But how are we going to draw that? That's too complicated to draw. So that's why we're kind of simplifying it and drawing it out like these individual structures just to see where the electrons are traveling. Actually, they are already there, but where are they? So these 2 electrons are basically, you can go from pi to positive. So here, you can take these 2 electrons, those are the pi electrons here, and then move them over here. So basically, you're going to now get a bond between these 2. The middle electron, we haven't really moved in a theoretical sense. Okay, although all of them are, all 3 here. So here, these over here have moved over here. And so therefore, there's nothing in here. This is empty. Earlier, this was empty. So now this becomes empty, so you have a plus here. So there's your pi. And this was your earlier, this was your pi. And it just moved over. So basically, if you were to rewrite this nicely without all those orbitals, all you did was go from pi to plus. And it looks like your plus jumps around, but pluses are really holes. That means there's nothing there. They can't really jump. It's the electrons that jump. And 2 electrons in a bond. So that's why you have a complete whole arrow. And then electron is just it's smeared. So therefore, this is happening constantly. Here's another one. We have here a pi, and you have a lone pair. Okay, here's your pi. So the pi can go on top there. So here, you can take this electron here, the pi electron here, and it can become a lone pair. So this is pi to lone pair. That's another very, very common trend. So here, if you draw this out, you have an oxygen, then you have 3 lone pairs here. You broke the pi bond here, so you're going to get a positive here. So you'll have an empty orbital. And 3 lone pair orbitals. So this goes up and you get a positive. Now you have 3 lone pairs here. So if you do the formal charge, you will get a negative here. So overall charge, plus and minus is 0. And this is also a neutral structure, which is 0. So overall charge won't change. Here, +1, +1. Over here, this is another trend, very similar to this, but here you have a lone pair and a pi. So should you push electrons this way or this way? Well, if you try to push electrons like this, there is no space on the oxygen. There's already an octet, and you cannot exceed 8. So you cannot do this. So you have to first think about where you are going to push electrons. Here's a pi and a pi, which means you have a p orbital and a p orbital, and a p orbital can take a maximum of 2 electrons because it's an orbital. So therefore you can move this over here. So the pi can move over here. Those electrons can move over here, which means you're going to have a positive here. So if I draw that in-between structure there, you'll have a positive. So here you'll put both electrons here and you'll get a negative. So that orbital is going to be negative. Remember, there are hydrogens. So if at the beginning you're wondering where it doesn't have any valence, put the hydrogens in so you will know that this is a negative. 1, 2, 3, 4, 5, 6, 7, 8. It's got an octet and it's got 5 in the box. So therefore it's a -1. So here you took off that electron, there's nothing here, and so therefore 4 minus 3 in the box is a +1. But that's a very bad structure because you have lots of different charges spread like that. So we don't typically draw this. We would draw the next one in one shot. So here this is going to go over here, and you will become a oxygen positive. And you might think, what? Oxygen positive? Oxygen so electron negative. How come this is going to be better than this? Well, more than the charge, the octet rule is the most important one. First, this is the first most important rule. This is the second most important rule. And then a minimum charge is the third one. So if you go in priority, that is going to be the best. And then neutral structures are the best. And more electronegative atom has negative charge. That is also very good. So that would be your fourth one. So there are priorities even for the rules. So octet here, all octet structure here, even here, is better than a no octet structure here. So if we were to rewrite this again, you're going from a lone pair to pi and pi to lone pair. And you will get a positive on your oxygen and a negative on your carbon. So this is just describing how it happened in stages, but this is lone pair to pi. So we have pi to lone pair to pi, pi to positive. And what about this? Where do we draw the line? Oh, well, over here, if you take this, oxygen has lone pairs, this is empty, and so the empty cannot really move anywhere. The lone pairs can actually move in there. So you might think again, oxygen is now going to be positive. Isn't that a bad thing? So you'll have a hydrogen there. Again, this is better. This overall structure is better because it's an all octet. So this is better than this. So here again, lone pair to positive. That's the next one. And over here, what do we have? We don't have any lone pairs. Where do we start? We can start at a pi. Pi becomes a pi, breaks this pi because there's too many here. Remember, there are hydrogens here. And so this pi will move over here, and that will move over there. Your p orbitals, so it looks like a sea of orbitals, 6 of them around that molecule, and so the electrons are just going around in circles. So here you're going to have this, just rearrange. So this is pi to pi. So these are typically the cases that you're going to see in any of this, any of the resonance. And we are going to apply that here. What do we have here? Well, we have something similar to this, pi to lone pair. Great, so let's do that. Okay, so I'm going to draw it over here. We have pi to lone pair over there. Okay. Now, please don't forget to put the charges, formal charges. Again, as we said, the charge of the molecule doesn't change, you know, and the electrons are just running around. But in these individual charges, because they are discrete Lewis structures, you still have to be mindful of the charges. So here 6 minus 7 in the box is going to be a -1. 4 minus 3 is a +1. Overall 0. So now we have this. Where do we go next? If I bring this back, which happens most of the time, and it's here because the neutral structure is the best, we're going to go back here. Let's try to do something new. So this is positive. I can take these electrons, and it's like swinging open a gate. It goes from here to here. So these electrons go over here, which means you're going to lose an electron from this carbon, and you're going to give it over here. So that is going to be over here, and you lost an electron here, so you'll have a positive here. This is nothing in here, so it's empty. And this becomes 0. This is still a -1 because you haven't changed this, and this is a +1. So it's still +1 -1, it's just that it's going to be spaced out. Now one more is going to be, again, it's like swinging a gate open. So you have a hinge here, the carbon here between this positive, and I just write the positive like this, and this pi. So the pi swings open here. So you can draw it like this, or you can draw it on the middle of the pi and say it's moving over. And you will get another one. And so now you will get, you have your empty orbital and positive. Now you can go back in the reverse. You can go from here to here, and here to here, and here to here, and go back here. Go in the reverse here. I'll just do that by doing one set of electrons that would go bam, bam, bam. So you should always be able to go to your parent structure. In all of the structures, your charge should be the same, in this case 0. And you should only move lone pairs and pi through the system. So we obeyed all of the rules there. Here we go. Here's another structure here. Where should we start? Here's a lone pair. So should we do lone pair to pi? Let's try that out. So remember, there are these hydrogens here. So can we do this? Never, because that means you are going to try to push 10 electrons in here. Never go into an sp3 carbon that's fully substituted. I mean, sp3 carbon, which is an anion, is fine. That can participate in resonance, but an sp3 carbon that has 4 bonds, never. So therefore, that's not going to work. So we got to go the other way. First of all, it says here, start from some place that's negative or that's a lone pair, and then move towards the others, which is why I'm trying to start here. So should we do this? Well, again, same problem. You cannot do this and do this at the same time, because that's going to give you the same bond. So if you do this, you're going from an electronegative to a more electropositive. That's also not a good thing. So therefore, this is also not a good thing. All right, so then where should we start? we can start by going to the electronegative group, like here, pi to lone pair, to the negative electronegative group. That's much better. So basically, you're just swinging this over here. Now nitrogen, let's see what happens over there. So you have a hydrogen, nitrogen, and then you have over here this electron on nitrogen. So you have 2 electrons, now you have 4 electrons on nitrogen. Is that okay? And you have nothing on the carbon. It's positive. Nitrogen's electronegative, more electronegative than carbon. So between carbon and nitrogen, nitrogen is in a better place to accept an electron. So nitrogen should have 5. It's got 6 in the box. So therefore it's a -1, and then this is a +1. So you have a 0. And this swings over, and you are going to get a new structure where your pi bond is now here, and you have a hole here. So the pi bond would move over here, and then this hydrogen is here, and there are 2 other carbon-carbon bonds, but it's lacking a 4th bond, and so therefore it's going to be positive. So negative on the nitrogen, positive on the carbon, overall 0, just like your starting structure. Now what do? Can we take this and move this over here? Never, right? Because sigma bonds cannot be broken. So now we got to go in the opposite direction in order to go back to our parent. So this comes back, we go here, and this comes back, and we go here. And I'm going to just do that, just like that. And then that's going to go up here. And this will go from here to here. So you should always be able to go back to your parent structure. In this case, that's the best structure because it's neutral. Here we have some charge distribution, but it's really minimal. So overall 0, and that doesn't change. Let's look at this one. Where do we even start? Do we break a bond here so that you have a nitrogen? Now, lone pair to pi, is that possible? No, you've never seen quadruple bond. Triple is the max. So you cannot go this way, obviously. There are 2 options. You can go pi to a lone pair, or this pi breaking up. Which one should you do? Well, let's look at some of the moves here that are forbidden, okay, prohibited moves. Then you can tell me which one you're going to do. So over here, you have some moves here that are forbidden. Now, if you take this, can we do this? Can we move this pi to a positive? Can we do that? Like this, but in this direction. Look what we get if we do that. If we do that, we're going to get a pi here, and your oxygen now is going to be 6 minus 5 plus 1. So this is never going to be acceptable. It's better to put the positive on the carbon. So this is bad. So you will never take a pi and move it over here to a positive if it's connected to an oxygen. So this is bad. Here's another one where let's say you have something like this. Should we just take a pi bond in the middle and break it up? It's really not a good idea to just start somewhere in the middle. Let's say you have a carbonyl here. Should you start here like this? If you do that, you're going to get a carbocation and a carbanion here, and this is going to violate the octet rule. No octet. So this is bad. But sometimes, if you don't have a choice, then you could do that. But it is really a bad structure. No octet. So try avoiding that. Over here, you can do the same thing. Should you do it here or should you do it here? This is actually a better resonance structure just because you have an oxygen here that's taking your minus. Then you can move this over here. But you should never do this. You should never do this. Take the lone pair and try to put it over here. That's going to violate the octet. So this is a big no. Over here, again, same thing. This is fine. Bring it over here, but you don't want to bring this over here. This is a big no-no, because you can't really break these sigma bonds. How about here? Can we take these lone pairs and go all the way? No, because they're not adjacent. How about the pi? Can I do this? No, because that is not resonance. If you do that and you follow your arrows, you are actually trying to make a bond here and put a positive here. So this is bad because, first of all, oxygens hate to be positive, very, very electronegative. After fluorine, oxygen's the most electronegative. So it has to be adjacent. So you can only move it to the next carbon. Like this, you can move it over here. This is fine, but you cannot go in the reverse direction. Oh, here's another one. Nitrogen. You got a positive. What does that mean? Does that mean it needs electrons? And can we do this then? If it needs electrons, a positive always needs electrons, right? It's always looking out for somebody, a negative. What about this? Well, over here, second period, maximum 8 electrons. So even though the nitrogen is a positive, it's got an octet. So this has an octet fill. There's no space for 2 more electrons. So don't be fooled by the nitrogen positive. You can't really push electrons into that. Here's a lone pair and a pi. Can we do this and do nice resonance over here? Again, same problem as here. You cannot skip an atom. There's a CH2 in between. You can't just overlook that and jump over here. This is actually going to be a reaction. Can only move electrons to adjacent carbons or adjacent atoms. This is really important. Okay, here it is. Here's an anion. And here you have a nitrogen here, and the nitrogen's got only 3 things. So, wait a minute, can't we just make a double bond and have it have an octet? Well, what they haven't shown you is this nitrogen actually is a lone pair. Because how do you know that? Because if it didn't have a lone pair, they would have put a positive there. So there's no positive here, which means it's neutral. If it's neutral, the formal charge is neutral. That means you got to have 5 things, 5 electrons, and there are 3 sticks and 2 lone pair electrons, 5. So this is the correct structure. Now can you move this in here? So you have 2 electrons here. Can you move this over here? No, you cannot, because it's already got an octet. So these are things that you shouldn't do. So if you see a nitrogen like that, and let's say a pi bond or something, or a lone pair, you cannot move it in here because this already has a lone pair. As a lone pair, that's invisible. Here you go. Here's another one, nitro group. So this means you have lone pairs here. This is a positive. Oh, here's a negative and a positive. Why are they standing apart? Why don't they join hands and become a neutral bond? Didn't we say neutral is the best? Well, look at it. Over here, the oxygen became neutral, but look at the nitrogen. It's got 2, 4, 6, 8, 10 electrons on nitrogen. You can't do that. So therefore, this is not possible. So even though you are looking at charges and trying to do this, this is not possible mainly because of the octet rule. So you have to make sure charges are correct, octet rule is all obeyed, and you're not breaking sigma. So let's take this molecule over here. If this is bad and you shouldn't start here, where should you start? it's best to start at the oxygen. So here, if you start at the oxygen, you are not going to violate octet rule. So here's an octet. Here's an oxygen positive, but it's got an octet. And then, you can keep going, so on and so forth. So if you have an opportunity to start at an atom and move electrons in a direction where you will have all octets, you should do that. You shouldn't just randomly break something in the middle like this and create bad Lewis structures. So this is not a good idea. This is a good idea. You're showing resonance overall, but with very beautiful octet-filled structures. So coming back here, where should you start? As you said, we shouldn't randomly start breaking things here. This electron flow is right here going over there. So then you do that. In this case, maybe you cannot really prevent it from having structures that are not octet. Now you can then go in and do the next one. So this is going to be your second best structure. And you could say these are the two main contributors. So here is a positive, and then you can move this over. And this is really not going to contribute as much, but that is a possibility. But these are the two main contributors. So over here, again, since we have discussed what are the things that we shouldn't do, where will you start? So we have choices here. We can take this and go in this direction, or you can start here and go in this direction. Which one? Are you going to go over here? No, because we just said that's not going to happen. That can't happen because you don't want 10 electrons in there. But you can do this. You can go over here and move that over there. That's possible because your valence state on the nitrogen is the same, because now you're going to break that and make it into a lone pair and make a pi. So these two actually look identical. The only way you will know that they are different is if you actually go in and put an oxygen label, and even then it's going to be hard. Then you can start moving stuff. So here, even though this is positive, it's got an octet, so it's perfectly fine. And here, if you don't want to break the middle carbon and create a carbon that doesn't have an octet, you can use your lone pair to do that. You can use your lone pair, go over here, and bump this to the side. So this is another octet structure that you can write without violating your rules, your octet rules. So it's going to go from a lone pair here to a pi, which is what we did. A lone pair to a pi, just like here. Now over here, you're going to have your nitrogen oxygen. So you put your negative, your 2 electrons from here. The pi became a lone pair. And now you can take those, and this is fine. This, I've redrawn this. This can go over here and kick this to the side, oxygen. So you can do these things without breaking an octet, violating your octet rule. So here your pi will become a lone pair. And then your lone pair here becomes a pi. But again, your nitrogen is only going to have 8 electrons, and your oxygens and all of the atoms. And even the oxygen here is only going to have 8 electrons. So you're not violating the octet in any of these structures. And you manage to do all of your resonance without violating octet rule. Which one is the best? Well, the best is going to be the one where we have minimal charge separation and the charges are on electronegative atoms. So here's a negative on the oxygen, negative on the oxygen. Nitrogen has positive in all of them, so we don't really have a choice on that. But here carbon has a negative. And then oxygen has a positive. So these are the best. These are the best. because here we're not really having anions on carbon or cations positive on oxygen. There you go. What about this? The reason I put this is I see all the time students going, okay, well, why don't we move this here and move this here? But remember, guys, there are 2 hydrogens here, so we cannot do this. That is impossible. You can put it on this carbon, that's okay, but you'll get a really bad resonance structure. So you'll have a positive here and a negative here. This is a really bad resonance structure, and so it's mostly going to be here. So even though these are possible resonance structures, 99% of the time it's going to be in this region. So there you go. So here's some resonance practice for you, and also showing you what are the things that you shouldn't do. So if you know what you shouldn't do, then it's a little easier to figure out what you should do. All right, guys, we will do a little bit more practice. If you need to, you can watch the next video, but I'm just going to put that on there just because resonance is such a huge part of acid-base chemistry, of stabilization, of intermediates, transition state, and the whole thing all the way to the end of the semester. So I'm going to put another one out there for you with a little bigger and more complicated molecules. So if you really need help, I would recommend that you watch that. If you got the concept, you're fine. Bye.